In the years around 1580, in the city of Florence, Italy, in the home of Giovanni de Bardi, Count of Vernio, a group of people came together to solve a common problem. They called themselves the Florentine Camerata. Their mission? To reform modern music. That music was polyphony, and it sounded like this. Very pretty. Now, polyphony consists of 4 or 5 melodies, all equally important, all entwined with each other, and it maximizes for a feeling of holiness. The Camerata dared to ask the revolutionary question, what if we could understand the words? Specifically, they wanted music with an optimum balance of words and music to convey an experience, to convey emotions, and like a whole range of emotions, not always holiness. The Camerata set out to do this. And what interests me about this group is how much they remind me of a modern Agile team. First of all, they're multidisciplinary. You've got musicians, like composers and singers, but you also have poets and astrologers and scientists and philosophers and noblemen and clergy, and they're all coming together in a group because they all care about solving this problem. They have sponsorship, so they met in the homes of Giovanni de Bardi and Jacopo Corsi. Okay, in some ways it was more like a meetup than a team, but roll with it. They had that common purpose that was very important, and they had agreed upon methods. How are we going to reform music? Well, back then, they thought history moved in a circle rather than a progression or a spiral. So to go forwards, you needed to go backwards. So they researched how the ancient Greeks set words to music. Now, it's not like they had recording, but the thing is, this lent legitimacy to their work, this method. So it's kind of like when I cite computer science papers from the 1970s. Caccini, the renowned singer, remarked that he learned more from their learned discussions than from 30 years of descant. Now, descant, I had to look that one up. It means lecturing, so what you're getting now. Fortunately, this conference is full of learned discussions. They met every week or two and they talked about this, but they didn't just talk, they also played music. So the Camerata was a laboratory for creation and performance. And they had code review. I like the part where the censors were nominated for the occasion. It wasn't always that asshole who hates you and takes it out on your code. They didn't all get along, though. I mean, the two sponsors, Bardi and Corsi, Bardi wanted to do more talking, and Corsi wanted to do more playing of music. And similarly, the musical stars, Caccini was like, it's about the music, with some words, and Perry is like, it's about the words, with some music. You know, your architects can't agree on everything. But a balance was achieved. The Camerata totally made history. They succeeded. They came up with the stile representativo, the radical innovation of a single melody with a little bit of musical accompaniment. Everything obvious wasn't always. And this style, it spread through their network of correspondence to Rome and Italy and the world, and then people were listening to this. Now, I still can't understand the words, but I don't speak Italian, and I'm told that if you do speak Italian, that doesn't help either, because this is ancient Italian. But back in the day, oh my gosh, people got it, and they felt it, and it spread through the world because it connected a whole generation of people with music. They couldn't have appreciated it otherwise. So the Camerata totally changed the world. I mean, they invented opera, which is how we mark the beginning of the Baroque era. It's huge, but that's not what interests me. What interests me is what happened with the individuals in the Camerata afterward, so after 1600. These are some of their publications from Wikipedia, and there's a couple operas on here, yeah, but there's philosophic and scientific treatises, and there's math. Vincenzo Galilei also contributed his son, Galileo. And these are fewer than half of the members of the Camerata who have Wikipedia articles today. They did not expect that in 16th century Florence. So that I found really fascinating, and I went looking for more information, and I came upon this paper, Collective Problem Solving in the History of Music, by Dr. Ruth Katz, musicologist, published in the Journal of the History of Ideas. This paper compares, oh, by the way, all the quotes in this presentation are from this paper unless otherwise attributed. And Dr. Katz compares the Camerata to the kind of invisible college that's known to be the source of progress in science. An invisible college is the group of people in your lab, or that you share a faculty lounge with, or that you correspond with. All the people who are working on a similar problem to you or criticizing your work. Invisible colleges are essential, and they have these characteristics. Okay, they have tacit understandings about appropriate methods of research, like the scientific method and research standards of the day. They have priority problems. That means fighting over who was first. More on that later. And they have this shorthand communication, a shared language, kind of like domain-driven design talks about the universal language. They're able to talk to each other, and therefore, when one of them hits on the right idea, they can spread it. Now, these are found throughout science. We love to tell the hero stories of the great discoverer, but really, that's not how it goes. For instance, we're taught in school that Benjamin Franklin discovered electricity. Franklin was a cool dude, and he did a lot of work, but he was building on and collaborating with dozens of, if not hundreds, of amateur electricians around the world. Lots of people were doing experiments about the unexplained phenomenon that we now call electricity and magnetism. And lots of false theories all built into his, which wound up working the best, and so he gets all the credit. Ben Franklin, one of his camaradas, was called the Club of Honest Whigs. So now we're up to around 1770 in London, and they met fortnightly in the London coffee house to dine and imbibe and discuss science, especially electricity, religion, politics, and other matters. This Camerata is described in a book about Joseph Priestley. So Joseph Priestley was a scientist in England. He's credited with the discovery of oxygen because he noticed it. He didn't do much with that, but he passed it to Lavoisier, who founded chemistry. He also contributed to ecology because he did a lot of experiments. He'd get a mouse, right, and he'd weigh it and put it in a jar and see how long it took to die. Sorry, mice. And then weigh it again. And he'd put a plant in a jar and see how long it took to die. And one day, he put a mouse and a plant in the same jar, and they didn't die nearly as soon. Now, this wasn't like appreciated until the 1920s, when ecology became a thing. But still, more currently, he also invented the carbonated beverage. He passed that to someone who made a lot of money. But Priestley was built up and encouraged by the Camerata, the Club of Honest Whigs. The other thing important about the London coffee house here was that this was during the Enlightenment, a time of great progress in the world. And one of the reasons for that was coffee. Like, coffee had just been imported into all of Europe, so people are drinking coffee with breakfast now instead of beer. Every discipline was new again, and whole new disciplines emerged. Of course, this also happens in art, and Dr. Katz talks about the salons in Paris and the coffee houses there, where you've got artists, but also critics and collectors and all the stakeholders in the art world, everyone who cares, coming together to talk about the latest advances. And in art, the idea of a common problem corresponds to a new artistic style. So the Impressionists answered the question, what if I painted not what is, but what I see? Here's a picture of one of those salons where they talked about this. This one, I took this in Paris when I went there, and its name is the Agile Bunny, except in French. And just down the street from that, here's a plaque on the side of a house, here's a big house, and here's a bunch of famous painters and poets and printmakers who happened to live there all the same time and then went on to become famous. Not a coincidence. One of the people who got a lot out of hanging out in Paris was Van Gogh. So here's a painting that Van Gogh did in the Netherlands, and there's a cabbage and a carrot, maybe, but not a lot of orange. Meanwhile, his brother Vincent is in Paris. No, his brother Theo is in Paris. And Theo is like, Vincent, you must come here. You have no idea what colors they're using. And eventually Vincent gets evicted in the Netherlands, so he does go to Paris. And sure enough, he learns all the colors that we associate with his paintings today. And Theo is like, wow, you have created for us a circle of artists and friends. And yeah, a lot of other painters grew and evolved with Van Gogh. I think Gogh here is the one he cut his ear off for. Toulouse-Lautrec, his paintings show up a generation later in the Salon of Gertrude Stein. Gertrude and her brother Leo were American, but they were living in Paris, and they had some money, so they fed a lot of artists. And Gertrude Stein had the first ever collection of modern art because modern art was just becoming a thing. She introduced Picasso to Matisse. They had a bit of a rivalry going. But the other people who came to her atelier, I think that means big room, for dinner on Saturday nights, Whitehead is a mathematician and philosopher, Apollinaire is a poet, and there's writers. A bunch of interesting people who were interested in what was going on in the day. Later, Picasso and Georges Braque, they found Cubism, which is the style that answers the question, what if I want to paint not just one perspective, but all the perspectives? Picasso is a rare artist who made money during his lifetime, so he ran a salon, and lots of people came in and out of that, including Henry Miller. He's a writer, and you've got photographers and philosophers. One of the painters who came through Picasso's salon was Alexandra Exter, and she was from Kiev, so she took what she learned back to Kiev, where she had her own salon, and these other Alexes went to high school with her and hung out in her salon. And Bogomazov, he painted this goat head, which is on my bedroom wall today. Ideas, they just get bigger as we pass them on. And I've seen this in software too. I've noticed from going to conferences that I keep running into other speakers on all different topics who, when I ask them about their history, they talk about being on this really cool team in ThoughtWorks London around 2003 to 2006. This team, they all worked at ThoughtWorks as consultants, but at different clients, but they came together to solve the problem of how do we deliver software in under 2 weeks and without hating life. And Jess went on to write a bunch more books about DevOps and continuous delivery. But meanwhile, Dan goes to create behavior-driven design, among other things. Nat Price is known for unit testing books. Sam Newman is the prophet of microservices. And they all came back, they all started in this one critical team. I also see it in the team that started Spring around the same time in London and across the world. Rod wrote the initial book, and the objective there, the problem statement, was how do we do enterprise Java without stabbing our eyes out? And they all came together to produce a software solution and a company, SpringSource, that solved that problem for people by not making humans write all this ridiculous amount of repetitive code. And like a couple years ago, I'm in an elevator at QCon London. I'm like, who's this Rob Harrop guy who's keynoting? And Rod and Christian, who work with me, are like, oh, well, we know him. Sure enough, you've got like the founder of Elasticsearch and venture capitalists and all kinds of things, all from this one same team. I gave this talk in Australia, and Kent Beck came up to me afterward. He was like, oh my gosh, have you heard of the Hillside Group? Because that was one of his early camaradas. And they came together on a hillside, among other places, Over a course of years, they were trying to solve the problem of, is it possible to write software such that 2 years later we can look at it and actually understand it? They had Christopher Alexander's architecture patterns to start with. So Ralph Johnson, he's one of the gang of 4 design patterns. Grady Booch is a progenitor of object-oriented programming. Ward Cunningham invented the wiki. Of course, Kent Beck goes on with others to start extreme programming and sign the Agile Manifesto. But these days, Martin Fowler is best known for refactoring, and Michael Feathers invented legacy code. The pattern repeats. The pattern keeps showing itself. That these teams have some sort of magic. You want to think that you can hire a bunch of great developers, put them together, and poof, get a great team. I've never seen that work. But what I have seen is the other way around. Great teams make great people. Great teams make great people. Okay, why? The next question is why. Because if we know why, then we could do it on purpose. I have a model for that, a theory, that also answers some of my other burning questions about software development, and I want to share it with you. It starts with Gregory Bateson. So Gregory Bateson, his father was William Bateson, who was a biologist who coined the term genetics, and along with a bunch of women in his lab, made genetics a thing in biology. So Gregory Bateson went into anthropology, but he also worked in zoology and psychology. He had a dozen octopuses in his living room for a year to study animal cognition. But one of his early camaradas was the Macy Conferences on Cybernetics, and you'll recognize some names here. John von Neumann, he created game theory and the basis of modern computer architecture, among many other things. Claude Shannon and Norbert Wiener did information theory. Margaret Mead, also an anthropologist. McCullough was a neurophysiologist, and Kurt Lewin is a famous psychologist. They came together like 9 times over 5 to 6 years. We're up to like 1950 here. And one of the things they talked about a lot was feedback loops and circular causality, and how could we take this newly recognized pattern and apply it in many different fields. The concept of feedback loops feeds into systems thinking. Gregory Bateson was huge in systems thinking. Systems thinking says that, look, you can't take a system, break it into parts, look at those parts individually, and get anything. You're missing the important bits, because the important bits are between the parts, in their relations and in the feedback loops between them. That's what makes the system. Bateson applied this in a lot of fields with a bunch of psychologists. He came up with the concept of the double bind and the idea of family therapy, the radical idea that maybe if we care about someone's psychological health, maybe we don't just go deeper into their individual head. Maybe their situation matters. Maybe their family is relevant to this. Everything now obvious wasn't always. So Bateson loved systems thinking. One of Gregory's other contributions is his daughter, Nora. Nora Bateson is also an anthropologist. So she grew up steeped in systems, in relationships, in deep context, in the idea that one perspective is not enough, we need many perspectives. And she says, this word systems is not cutting it anymore. Because when you think about a system, you might think about something mechanical, like a big machine or assembly line that, you need to understand the parts and how they interrelate, but if you got all of that and enough formulas and put them into the computer, you could master it. They tried to do this with ecosystems in the 50s and 60s, so now you've got dozens of grad students spending thousands of hours cordoning off square meters of prairie, counting the blades of grass, separating the bugs into species, and then weighing them, and then burning them, and then weighing them again. Because they thought that if they just got enough numbers and formulas into the computer, they could master the ecosystem. They could predict outcomes and how to intervene constructively, and it never worked. That's not how it goes. Because those species don't hold still. They don't relate the same from year to year or month to month. They're constantly evolving. and they're constantly finding new niches and generating new species. The whole ecosystem is learning, and the parts of it are learning from each other. So Nora says, look, when you've got a learning system made of learning parts, that's something different that we don't necessarily associate with this word system. We need a new word for it. So she coined the term symathesy, from the Latin sim, together, and mathesy, learning. And a symathesy is a system where all the parts are constantly learning from each other, which enables the system as a whole to learn. This is an extremely powerful concept. Okay, so we know a system is not the sum of its parts. That would be an aggregate. From Ackoff, we have it's also a product of their interactions. Yeah. But Nora Bateson points out that the parts are a product of past interactions. That's a symathesy. This is really powerful. There are no zero-sum games in a symathesy. For me to win, you also have to win. Of course, our teams fit this. We know our teams are not an aggregate. We're more than the people, and the environment represents like your desks and chairs and stuff, the leafy thing here. Our relationships matter too. Thank you, Agile. Yes, we communicate. But also, we're each colored by our past interactions with each other. I am the product of many teams and families and communities that I've been a part of. So yeah, our teams are symatheses. And here's the thing. I think a software team is even more of a symathesy than other human teams. Because with software, it's not just the people involved. So for my team to succeed, we need to be operating useful software in production. And that takes the people, and it takes that software running in production. That running software is essential to completing our success criteria. And it learns from us because we change it, that's our job, and we learn from it. We learn from the exceptions that it throws, the data that it changed, the event traces. So the running software is participating in the symathesy. Now, we don't learn from it directly. We need our SQL queries, our event aggregators, our screens, and our logs. And it doesn't learn from us directly. We need our IDEs and our source control and our deployment pipeline and our automated tests. So the tools are essential. We only learn through the tools. We learn when the test fails. And the tool learns from us because we change it. We add automated tests. We write SQL queries. Hopefully, we can improve our deployment pipeline and add entirely new automations because we have that power. As developers, we work on the computer and we work in the computer. We can change the world we live in. So the tools are part of the symathesy. It's one big socio-technical system, if you want an even longer but older word. This answers a couple questions for me. One, why do I need to be able to bring my whole self to work? Well, to be part of a living, learning system, I need to be alive in it. And also, when I look at all the interrelations here, and I did not picture very many of them, this is like way simplified. When I think about how many connections there are that are important, I start to understand why this is so hard. Because in 20 years of software development, it has not gotten easier. It's only gotten more interesting. Now, it wasn't always so complicated, at least I didn't feel it. When I first started developing, it was just me and the piece of the system that I worked on, which was pretty small, and somebody handed me the requirements, make it do this thing, okay, I'll make it do that thing. And when I needed some data, I said, how do we use the database? And they gave me a book on Oracle. Just kidding, I bought it myself. But that was it. It was kind of a closed world, or I felt like it was. Not anymore. These days, I'm like, oh, we need to keep some state here. Which database shall we use? Or databases? How shall we do migrations and backups? And do we need caching? My scope that I look at is a lot wider, and my influence is a lot wider. I'm able to think about more and change more about the system. And this tells me what it means to be a senior developer, or an enterprise architect, or a high-level individual contributor, whatever you want to call them. The senior developer thinks even more widely and influences even more widely. So the senior dev knows about the systems that our system connects to, the infrastructure our system runs on, and what the purposes of those systems are, and knows people on those teams. Because we're always going to need some of the knowledge that they have. The senior dev also knows people outside the company, like meeting them at conferences, because you never have all of the knowledge that you need in-house, and you need people to ask. Another reason this is important is that our team needs to have influence on the other teams. It's a thing that you can't take a team and say, you, go self-organize in this box, and don't bother us. Just keep to yourselves. That's not how it works. Because we are impacted by other teams, and other teams are impacted by us, and that's healthy because we're learning from what they're doing, they're learning from what we're doing. We don't control them, but we need to influence them. And the organization as a whole is learning from this. It's symatheses all the way up. There's one more thing I need to add to this diagram, and then I'll pretend it's complete. And that is a big red line between the human and the digital space. Because if I want to learn from my coworker, I can be like, yo, what's going on? I can tap him on the shoulder, ping him in Slack. What are you doing? Oh, here's what I'm doing. Maybe we'll adjust. But if I want to know what the software is doing, I can't just look down and see what's going on in there. I am limited to my screens and my keyboards until Tron is a thing. I can't get down there and kick it to make it do something different. I am limited to my IDEs and my deploy buttons. All we have is these representations of the software. This is called, this barrier is called the line of representation because that's all that gets through. What's going on in our software? Well, I can look at the app screens, I can look at my event tracing, I can look at the database, I can look at the exceptions or the logs, but all of these are just representations of what's going on. I can look at the code, that's another representation, and then I can change the code and push that through into source control and the deployment pipeline, and that represents what I want the software to do next. This line of representation is a barrier to learning in the system, in the symathese. It's a tricky one, and in particular, it makes it really hard to get an accurate mental model of the system. Because when we're doing our work, and let me be specific here, our work is not typing. You can tell because we don't type all day, and most of what we type we delete. Our work is making decisions. What to type, what questions to ask, what to look at, what to change next, what buttons to push. Decisions are the hard part, and those decisions are based on knowledge, including our mental model of the system. And here's the thing, because of that barrier, because we can't look at it directly and really see what's going on, those mental models are never perfect. Woods' law says that for any system of sufficient complexity, and we're way past that in our software, everyone's mental model is necessarily incomplete and out of date. And everyone's mental model is incomplete and out of date in different ways. Now, that part has its advantages because there's a reason we have a team, and it's because this whole system doesn't fit in one person's head. In his book, Why Information Grows, Cesar Hidalgo, who's a statistical physicist, talks about the concept of a person byte. A person byte is the maximum amount of information you can cram into one person's head over their lifetime. Doesn't matter how much that is. Matters is that it's finite. Our brains do not scale infinitely. We have to go outward. We have to form a team. And in that team, we need overlapping mental models. We need that shared language of communication. But then we also need diversity of knowledge so that collectively we can maybe come up with some idea of what's going on in the software. It doesn't matter just what is, it matters what we see, because that's how we make decisions. These mental models are super valuable, they're how we do our work, and they're super hard to acquire. I started to appreciate how hard when I read the book Vehicles by Valentino Breitenberg, 1970 philosopher, and he illustrates the law of downhill invention, uphill analysis. Okay, so this says that if you start with a system that you're building and it starts out simple, they all start out simple, and then you add features and you add complications and you add complexity and you make it more and more interesting, that is easier. And you build up your mental model as you go, as you're building it. That is so much easier than coming to an existing, working, complex system and gaining an understanding of it. That is really, really hard. It's counterintuitive, but it does explain the thousands of JavaScript frameworks. Because it really is easier. Oh, I just needed to do this one thing. I don't need all this other cruft. You make it do that one thing, and then the next thing that you need, and then the next thing that you need, and then and every step here is obvious to you and no one else in the entire world. But that is easier. It's not less work, it's not less typing, but it's easier to build your own JavaScript framework and build it up in your head than it is to learn React. Despite the hundreds of people who spent thousands of hours on documentation, on tutorials, on API design, on making this as approachable as possible, you're still starting from the bottom of the hill. And mentally, it's more challenging to learn React than to write your own JavaScript framework. So these mental models are really hard to build, and they're really crucial. This leads to situations like this. Okay, here you have a piece of the system, and you have Purple Developer. Purple Developer has a great model, great mental model of how that system works. They probably wrote it. But maybe Purple's been making some changes, but maybe they want to go on and do something else, or maybe we need more people on this, we think. And so here come Blue and Green. Blue and Green have been assigned to this project, probably part-time, and they don't have a good mental model. So they come in, and they're trying to gain understanding as they work. Meanwhile, Purple is churning through tickets and making changes, and it is very, very possible, and even likely, that Purple can change the system so fast that no matter how hard they work, no matter how smart they are, Blue and Green will never get a solid mental model of it. Never. I've been in that situation. Meanwhile, Purple's over here looking like a 10x developer, being like, what's wrong with those morons? Everything takes them a week and then they get it wrong. There's one solution to this, and that requires Purple to take their hands off the keyboard, stop making changes to the system except through the hands of Blue and Green. Pair programming, or even better, mob programming. This way, Blue and Green get the chance to ask questions. How did you know to look there? How would you test that? Oh, what about this thing over here? Oh, I was going to delete that. Don't worry about that. I would have lost days. Purple learns what was not obvious. But is Purple going to do that if what they're rewarded for is closing tickets? If these developers are stack ranked, why would Purple bother transferring their mental model over to Blue and Green? Why would they take that time to work alongside them, which is the only way these mental models transfer? So this gets back to those priority problems. The conflict between individual and group interests in an invisible college and in a team. In science, it's about who's first. Norbert Wiener and Claude Shannon both invented information theory. Shannon published it first. He's the name we know. Newton and Leibniz both working on the calculus. They wanted to share, so they'd send each other messages in a secret code that, not sharing the key or anything. No, if you could decode my message, then. If you do all that work, then maybe you'll be slowed down enough that I can publish first. That's not what I want in my team. I don't want to conserve ideas. Because ideas are not like matter and energy. This is not zero sum. If I give you an idea, I don't not have it anymore. It gets bigger. You're going to make it better. Ideas grow with sharing. Like Coraline mentioned today, she quoted that transferring knowledge is multiplicative. It gets bigger as we share it. And that's what I want in my team. Because I want my team to grow. And what does it mean to grow this kind of team, a software team? Now, if it were an aggregate, we would grow the team by adding people. But we know that all those people need relationships with each other, and those matter, and this is a system. And how do you grow a system? Well, it depends. In the economy is definitely a symathesis, but when we measure the size of the economy, we don't talk about geographic area, we don't even talk about the quantity of money in circulation, we talk about flows. So if I buy coffee for $5 and the coffee shop pays the barista, who pays the rent, who pays a plumber, that's $20 added to GDP. It's about the flows of money through the system. That indicates the size of the system. More flows, bigger economy. In ecology, they measure the size of the prairie ecosystem, not by geography, but by flows of a key nutrient, carbon, nitrogen, phosphorus, whatever's limiting. In this case, it's carbon, and this is why they're burning the bugs, to find out how much carbon is in each species, because it's carbon flows between each species that represent the magnitude, the richness, the meat of the ecosystem. And it gets bigger by adding more species and by increasing the flows. So our team, as a symathesis, if it's a system based on flows of learning, then we grow our team by growing the flows of learning, especially across the line of representation, because that's a bottleneck. But purple grows by moving that mental model to blue and green, by increasing the size of the team. And that is how purple is going to be a real 10x developer instead of just looking like it. It's one of those oblique goals. To be great, put the team first, and the team will make you a great developer. It's like happiness. You can't just aim for happiness. You have to do something that happens to make you happy. You have to produce something that happens to make a profit as a business. To become great, put the team first. And if you think you can't hire enough great developers, look inward, because great developers aren't born. And they're not trained. You can only get so much from college and YouTube. Great developers are symathesized. This is the point that I wanted to get to in this talk. This is what led me to go research the Camerata. This is the similarity that I saw between those software teams and this team from the Renaissance. But as I was reading the paper about collective problem solving, I came upon something else, something that surprised me and made me say, wait, what? And gave me an even more audacious idea. And I want to share that with you. It starts with the surrounding culture. So the Camerata were in Florence, the center of the Renaissance, at the height of the Renaissance. And there was innovation in the air. Side note on the word innovation, back in the days of Priestley and Franklin, the word innovation was had a negative connotation. It meant something that was going to disrupt the existing order, and that was bad back then. But Priestley and like Thomas Jefferson and John Adams, whom he corresponded with, in the age of reason, they were like, we can use reason to come up with ideas that will improve the current system, that will make it better. And now that's what innovation means now, something that improves on the current system. And that's the sense Dr. Katz used it here. Because the Camerata were like midwives to a century full of social and political and cultural ideas from which opera emerged. Indeed, one of those ideas was about systematic testing and measurement. So the scientific method is just beginning to become a thing. Vincenzo Galilei was the first known person to rigorously measure the length of string and the weight on the string, that if you stretch it out, you get a note, bing, 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 pretend that's a C, and then if he increased the weight until bing, 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 he gets the same C an octave higher, and then he might shorten the string, bing, bing, bing. And so he measured what it took to get notes at different octaves and chords and stuff like that, and he found consistent ratios between them, and he brought the math into music. I'm sure that was useful to the Camerata somehow. Meanwhile, in the Enlightenment, in Priestley's days, they had new ways of thinking about the world. They had empiricism, the idea that you could form a hypothesis about how it worked, reason from that what that would imply until you got to something you could test. Today, we have new ways of thinking about the world. We have computers. We can do math that we couldn't before because we can offload those calculations from our brains to software. Back then, in the Camerata, they had the printing press to disseminate knowledge. We have the internet for maximum knowledge dissemination. But dissemination is not enough because you can only fit so much in one human head. It takes a team of people to hold all the knowledge that we need. And that is the other thing about the surrounding culture. The very existence of such groups as the Camerata was new. It was new. And one of the things that made it possible for the singers and the poets and the scientists and the philosophers to all be in a room together was the recognition of art, with a capital A, as a thing. And this is the part that made me say, wait, what? There was a time when art wasn't a thing? I mean, I go to the art museum and I see statues from like 5,000 years ago. They're not pretty, but they're definitely art. That's the thing. Yeah, people were doing sculpting and painting and playing music, but those were crafts. In the Middle Ages, painters were craftsmen, and they joined the painting guild. And you got into the painting guild because your dad was in the painting guild. It wasn't about talent. And at the end of the day, you went home and then you had a beer with the other painters in the painting guild, or maybe the goldsmiths, which are the next guild over. And the sculptors hung out with the bricklayers. It was just a craft. Now, the positive was you got basic competence. So if you hired a painter, you could be pretty sure that they could come up with a reasonable facsimile of what you asked for. But then, during the Renaissance, you start getting painters that are working outside the guilds, that just have a passion for it, and maybe they specialize in like landscapes, sculptures of people, or cupids on ceilings. And you've got merchants who can hire these artists as they gain prestige. You start to get excellence. It's a little riskier. Not everybody has a computer science degree anymore. But then people noticed that there was some common thread between sculpting, music, painting, poetry. There was some common thread, and they didn't have a name for it. I think today we would say creativity. But they knew that it was ineffable and it couldn't be taught. And that gave it prestige. So now you've got these artists having prestige, and they're studying in academies with other artists in different areas and philosophers. And then they're in these cultured circles like the Camerata. Suddenly, the painters, the musicians, the composers have status. And you get to talk to them, and the Camerata became possible. The Renaissance was a time of transformation of homogeneous artistic circles into cultured circles. So the painters aren't just talking to painters anymore. And it was a period of decompartmentalization, breaking down barriers that kept things in order but also apart. Programmers, testers, operations. Given enough time, you might get what you asked for from that arrangement, but you will not get what you need. And the new style emphasized expressive qualities, impact on the world, over beauty of design and craftsman, code coverage, design patterns. I want my software to be useful and grow more useful over time, and that is what I care about. Software is not a craft, and I am not a craftsperson. Now, programming is a skill, and it is a crucial skill, and we need it, and we need to be good at it. A painter needs to know how to hold a brush and mix paints and pull a canvas, back then at least. But Java, it's acrylic paint. Ruby is like watercolor. Bash is a song on a loop, a hurdy-gurdy. Don't put it in your orchestra. This is an essential skill. We can't do our work without it, but it is not the essence of what we do. Now, I'm also not saying that software is art, okay? art has an impact on the world. If I listen to a symphony or look at a painting, it can have an impact on me, and that changes how I interact with the world and so on. Software is so much more direct. We change physics. Okay, if I pick up this box and I move my finger just right, a car shows up and takes me where I want to go. That is amazing. That did not happen 5 years ago. Now, it takes people too. It's not just software. It takes socio-technical systems. But code is an essential part of that change in the world. Code as a medium is unlike anything we've ever worked with before. It's more moldable than metal. It's more flexible than plastic. You can almost design right into it. And the feedback loops. We don't have to wait 15 years to see if the bridge falls down, or 10 years to see if people like that house or it holds its value. We can get feedback on whether this worked in seconds from our unit tests, in days from our web app, in weeks or months at the most, not decades. We can learn so much faster, and we can learn how to work with a complex system that's too big to fit in a single person's head. And we are. This is different. So I'm not saying that software is art. I'm saying that software is the next thing after art that we don't have a name for yet. The closest I can come in words is that ongoing software development is the practice of semathesy. And that makes me a semathicist in the medium of code. Now, I really like this slide, except for one thing. It has my name on it. An idea doesn't belong to a person. It takes a camerata, and then a community, and then a culture to make it real in the world. So we are all semathicists if we choose to think of ourselves that way. I am thrilled to be alive right now and in software, because software is the next thing after art, and this is the next age after the Renaissance. We have new ways of thinking about the world and new ways of changing the world.
If we manage to get this right, they'll surrender by early night.
The world will never be the same.
Oh, Alexander.
That's my daughter Evelyn singing Hamilton, the modern opera. May our work have such an impact 400 years from now. Thank you.